Okay, so hopefully you're here for what's new in the macOS SMB client. If you're not here for that, you're in the wrong room. So, start off with, who am I? As you can tell, I'm actually in that photo somewhere. When you have time later, it's like, where's Waldo? You can see if you can find me. So a little bit of my background. I'm a network file system engineer for Apple. I started back in late 1989. And I started as a QA engineer. That's why I'm so good at finding bugs. I switched over to development engineer, and they promptly took all the bugs that I found and assigned it to me to fix. The very first project I worked on was the Macintosh 2FX. And as you can tell from the specs, it was the Motorola 68030 at an astounding 40 megahertz. You had 4 megabytes of RAM. You could expand it to 128 megabytes of RAM. And you had your choice of an 80 or 160 megabyte hard disk drive. And it was running System 6.x. Quite a bit of System 6.x was actually in the Motorola assembly code. Oh, and if you look at my badge, that is not a Linux penguin. That is Opus from Bloom County. And I still have Opus sitting in my office when I program. So today, what are we going to cover? So it's been about 2 years since I gave this speech, so we've shipped about 2 OSs. We actually just shipped Sequoia, I think, on Monday. So I'm going to go over some of the changes that we made in Sonoma, some of the signing stuff that we added, some housekeeping work on the nsmb.conf file, a new option that we call connect to share disk. We also added nanosecond time support. Then we'll transition into the current shipping OS, which is Sequoia. And we made some directory enumeration changes to hopefully make it faster. We added client-side RSS support. And we added SMB compression. And if we have time, we'll do questions. And maybe I'll answer. So we'll start off with the signing algorithms. Again, an old newspaper clipping. This is all stuff that I actually have in my office, by the way. So this was about 10 months before, I guess, Michael Spindler took over as CEO and John Scully got pushed out. And this was a big comm meeting, and you can see I'm there in the front, and it looks like I'm sound asleep. I'm assuming it was just the, bad millisecond when my eyes happened to be closed, but. So, this is Sonoma and later. We added the new negotiate context for the citing capabilities. We now support AES GMAC, AES CMAC. And we added into the nsmb.conf some ways you can control it. So we have the typical signing algorithm map, so you can enable or disable the various signing algorithms. By default, we have both of these enabled with GMAC listed first. The old HMAC SHA-256 is still supported in, was it SMB2 protocol? So if you don't support these two, we will fall back to the old one. So some house cleaning stuff that we did. Just a note on the photo, these are the programming books that I used to use a long time ago. The Inside Mac whole series of books, I forget, there was like 9 or 10 of them. For me, it was the Files and Networking one. Of course, the K&R C book, 2nd edition. At that time, I was doing AppleTalk work, so Inside AppleTalk was the equivalent of the SMB2 protocol spec. It was the Bible. And then when we started doing OS 10.0, The book that we all had was the 4.4 Red Devil BSD Unix book. We all lived on this book. So what happened is, in Sonoma, we realized that a bunch of these keywords weren't quite in the right sections anymore, and so we did some house cleaning. So the nsmb.conf file has 3 sections. We have default, which is kind of like global, affects everybody all the time. We have a server-only section, so you could say, oh, this preference only applies to this particular server you're connecting to. And then we had another section which is server and share. So you could say, well, this preference only affects to that server and that particular share. So we moved some from the global section, the default, to default or server. So like protocol version map, which meant that you could say, I'm going to set the protocol version map for this server and it can only support SMB 3.1. And then this server over here, it can only do 3.0, okay? Versus when it was only in the default section, it applied for every single server you connected to. So, same thing with signing required and signing required versions. Again, you can specify it now to a specific server if you want to. The old validate, negotiate off if you're I think that's what, SMB 3.0, 3.02. The encryption cipher maps, that essentially defines what encryption algorithms are supported by that server. So if a particular server, you want to only advertise a particular type of encryption, you can do it now. The force encryption options have also been moved to the server section. So now you could say, this server over here, we always want to have encryption to, no matter what. But these servers over here, we don't care. Encryption is optional. The multi-channel ones, they actually happen to be in the server share section, which didn't make sense because multi-channel is more of a server ability. So we moved that actually up to the server section. Okay, so have to give a little bit of background information before I can talk about the next one. So Apple Silicon computers, they have what's called shared disk mode. The Intel computers used to have something called target disk mode. And the idea is if you were trying to recover data off of your computer where the OS won't boot anymore, you could boot in recovery mode. When you boot a Apple Silicon computer in recovery mode, there's actually an extra option. And it says, turn on share disk mode. And what happens is the Apple Silicon computer will be visible to another client computer that's directly connected over either USB, USB-C, or a Thunderbolt cable. And the client, so the Apple Silicon computer ends up as an SMB server. The client computer that you connect to it is coming in over guest. That client computer can see all the files on the Apple Silicon one. So again, the idea is your Apple Silicon computer won't boot for some reason, but you want to copy files off of it. Boot in recovery mode, connect a USB cable to it, put it in share disk mode, and then you can start accessing all the files off of it. Okay, so it's mainly for recovery. No, it has to be USB, USB-C, or it has to be a direct cable connect. It doesn't do it over the network. Okay, because we don't want to do it over the network because it's just too insecure. Yeah. Yep. And it was kind of analogous to the target disk mode, because target disk mode you would have to connect either a USB-C cable or a FireWire cable, and it would show up as an external hard drive just to that computer. Okay. So the key point is the client computers use guest to log in as. Okay. The NSMB.conf had a min auth preference where you could say, hey, only Kerberos is allowed or anything higher than that. But it didn't take effect because guest was being used. So that resulted in this new NSMB.conf keyword. It's called connect to share disk. It's actually a security option. You can set it to be yes or no, and essentially it allows or disallows a client to be able to connect to another computer which is in the shared disk mode. So the reason why we did this is you have a corporate computer. You've locked it down. So it's not allowed to copy data to any external storage. So if you try and hook up an external hard drive, you can't copy data off of it. If you try and copy it over the network, it won't let you copy over the network. Well, what happened is somebody has their own personal Apple Silicon computer. They put it into shared disk mode. Okay, so it's the server now. They connect it to your corporate computer, and then they were able to copy files from their secret corporate computer hard drive stuff to the Apple Silicon device. So that was actually a security hole. We're like, oh, yeah, let's not allow that. So for the computers, you can now set it up so that you can set a preference which says connect to shared disk is not allowed. And then now it's one less way of copying data off of your secure corporate computer. Going on to nanosecond support. Those are actually Apple design speakers from about 1993. And they actually still work. So nanosecond support. So in macOS Ventura and earlier, when we would look at SMB time, we would convert it to local file system time. We actually only converted the seconds field, and we ignored the nanoseconds field. So starting in Sonoma, we actually now convert the seconds and the nanoseconds time fields from SMB to the local file system, and vice versa, back. The thing that's kind of interesting is that SMB time is actually in 100 nanosecond intervals. So you have to do a little bit more math. This actually helps make some checks better. Like when we look at last write time to determine like local file caching. Like an example is 2 people are accessing the same file on the server and one guy has it cached. We actually make some checks every now and then. We say, has the file mod date changed or the file size changed and we didn't do the change? If so, somebody else either on the server changed the file or another SMB client came in and changed the file. And so having the nanosecond time intervals makes it easier to catch stuff like that. The other one is last change time. And I mentioned last change time because the macOS client actually uses that for the local caching for Mac's, the Mac's access and X-adders caching. I had a question earlier where they were like, if I change X-adders on the server, the macOS client that's logged in immediately noticed that the X-adders had changed. And they were wondering how we did that, and it was through the change time. And their particular server wasn't updating the change time. And so we would say, well, the last time we checked, there was no X-adders. We assume there's still no X-adders. So change time is important for us. Okay, so now we're moving into Sequoia. Okay. For those of you who remember, we used to have to install software with CDs and DVDs. So I have, it's macOS Jaguar 10.10.26, macOS Panther 10.3.5, macOS Tiger 10.4, macOS Snow Leopard 10.6, an iTunes 3, and I guess, what is it? iPhotos 2, iMovies 3 install CD. And then that's a fun one. It's a MacBook Air USB reinstall thumb drive. So the early MacBook Airs didn't have a CD drive. And so if you crashed your MacBook Air and you wanted to reinstall the software, you couldn't put a disk in it. And so when we shipped those computers, you actually got a USB thumb drive. And it had the OS on it, and you would plug it in there, and that's how you would restore it.
Read or read only?
Read only. So, previous to Sequoia, when we would do enumeration, so the client has a local directory enumeration cache, and it can only fit a certain number of entries, and it's actually based upon how much memory is in the system. We had a problem, well, I guess the way it currently works is we open the directory, we send the query DIRs, we parse out each reply, we add it into the enumeration cache, we add it to the user buffer to return, and then we keep doing that until the user buffer is full, and then we return out. If the total number of entries in the directory was smaller than the enumeration cache, we're fine. It all fits in the cache and we're good. The problem comes when the directory number of entries is huge, like 10,000 or something like that, and our cache only holds like the first 1,000. What we would do is the next time the enumerate came in and we were past the end of our directory cache, we would actually close the directory, reopen the directory, restart the enumeration from the beginning, enumerate all the way until we got to our last resume entry, and then we would start returning those. And then again, we would keep doing that over and over and over. So what you would see is you would see us constantly closing the directory, reopening the directory to start it again, going further down, returning those, and then again and again. And turns out some servers, when you close and restart a directory enumeration at the beginning, there can be a huge delay. And the more entries you had in the directory, the worse the problem became. So in Sequoia, the way we fixed it is it all kind of starts the same. You open the directory, send the query DIRs, you parse out the replies, you stuff it in your cache, keep going. But this time, all the extra query DIR replies that we've received so far, we just save. We say, well, we haven't gotten to these yet because the user buffer is full. We'll get to them soon. When we get the next enumerate request, we go, well, we have these saved query DIR replies. We'll continue to parse them and pull out the data from them and return it to the user. When we run out of the saved query DIR replies, then we just issue the next query DIR request, which again continues their enumeration. So what you should now see is the open DIR, the query DIR, bunch more query DIRs as we need it, and then eventually just the final close DIR. So we never have to restart the enumeration. Steve.
I don't remember exactly if Windows does this, but one of the Windows developers mentioned that the better behavior is to do open DIR, query DIR, so 2 query DIRs, because 99 point whatever % of the time that means you're done. And it saves a round trip 99% of the time. Do open query DIR, to do 2 query DIRs, because the second one is going to return no more files. In a compound. And I don't know, does Apple do that?
So the question is it better to do a open DIR, query DIR with the expectation that the second query DIR will get the end of, I think it's end of file, saying that there's no more entries in there? And does Apple do that? No, we do not do that. I have been looking at it. I've thought that's a really cool idea, but we don't at this time. Yeah, no, I totally agree. It's just haven't done it yet. Let's see. Oh, so even for servers that don't have the AAPL create context stuff and the reader adder stuff, we still do the same behavior. So it should make enumeration for all servers faster. And again, this only applies for directories which are really big, okay, that exceed that directory enumeration cache for that directory. So moving on into Sequoia, so we also have multi-channel client-side RSS. Does anybody even know what these are? Very good, eyesights. Do you still have? I still have one too. So I don't have the cables or the mounts. So the eyesights were back from 2003. It actually worked with a product called iChat AV, and it was the equivalent of like FaceTime today. It was a web camera, and you could do video conferencing back in 2003. You could actually even use it for filming movies, as long as you had a long enough cable and you could like move it around. I remember doing FaceTime on it all the time. I was like, this is great. Well, and then iChat AV eventually became FaceTime. And there was a little bit of time where they would call the front-facing camera FaceTime camera and the rear-facing camera the eyesight camera. And then eventually they just said it's all FaceTime cameras. So, client-side RSS support. In previous to Sequoia, we had a multi-channel limitation that one SMB channel was allowed per client NIC. But in Sequoia, if the client NIC, or I guess the client NIC driver, supports RSS, then we'll allow up to 4 SMB channels on that single NIC by default. You can increase it, decrease it if you want. You can use the SMB util multi-channel command, and it'll tell you if both the client or the server supports RSS. And again, in nsmb.conf, we added some more options so you can control it. So you can have max total number of channels, and that includes over multiple NICs. You can have max server RSS channels and max client RSS channels, and that's per NIC. So why did we do this? Well, it actually allows some flexibility in the selection of the channels between the client and the server, especially when you have different speed NICs and they're all in the same network. And I'll get into an example. It also allows more SMB channels between a client RSS NIC and a server RSS NIC. So previously, if the server had RSS, but the client only had one NIC, we would only establish one channel. But now you can establish up to 4 channels on that NIC. So let's go over an example. So the client has a 10 gig NIC and a 100 gig NIC. And the server has the same, a 10 and a 100. They're all capable of RSS. In Sonoma, what would happen is the client would try and connect the 10 to the 100 and the 10 to the 10, and also the 100 to the 100 and the 100 to the 10. But we do this all in parallel. So it's very possible that the connection from the 100 from the client to the 10 actually completes first. And then as soon as we would establish a channel, we would say that NIC is no longer available for other channel selection. So the 100 on the client gets connected to the 10 on the server, and we say, well, that's channel 1. The second channel, it says, well, the only thing that's left is the 10 on the client and the 100 on the server, so we'll establish that. So we end up with 2 channels, but the highest common speed between the NICs is only 10 gigs. So we ended up with 2 active 10 gig channels, which is not great.
What Apple device can take 100 gig?
The question is, what Apple device can take 100 gigs? Anything that take cards. Adult cards go up to 100 gig. So Mac Pros, Studios, I don't know, anything that can take a card. So with Sequoia, now what happens is the 100 gig on the client, he'll connect to, or he'll try and connect to the 100 gig on the server, he'll try and connect to the 10 gig on the server. Same thing, the 10 gig on the client will try and connect to the 100, and he'll try and connect to the 10 gig. But if one channel actually gets established, it doesn't prevent us from trying to find other channels that we can put together. So we'll do a whole bunch of connections, and then we'll try and figure out, well, what is the fastest links that we have? And so ultimately, we end up with the 100 connected to the 100, and the 10 connected to the 100. And if we did have ones that crossed, we would just drop them, saying, well, this is not very optimal. We don't really like this. And then again, since we now have RSS, we will establish 4 channels over that 100 gig link. It's
Quick question. So once it's established a connection, it continues to seek if there's better connections out there. How long
Yeah.
does that go on?
It depends on how many NICs you have. If you had 50 NICs on both sides, it could take a little while. But I mean, you've already established the first channel, so you're already talking. Okay, we're just trying to add more channels. So you could have a lot of combinations, but it is mitigated a little bit by the fact that we know what the fastest active channel speed is. And so we're always looking, is there a faster combination than that? Okay? So like as soon as we establish, let's say we crossed and we had 10 gig. We're like, well, I see a possibility of 100 gig. So it'll only try connections to like the faster ones. It won't try every possible combination.
But it's also dependent upon the network topology, is it not?
Yes, the question is, it's also dependent on the network topology? Yes, very correct. If you have separate networks for your 100 gig and your 10 gig, then it's not a problem. So. And again, this is from a presentation from 2 years ago, we always figure out what is the fastest active channels that we establish, and we use those, and then we keep one inactive channel, which is the next fastest. So if all the active ones fail, then we'll drop down to the inactive one, and then we start all the trial connections again, where we try and find what other links can we now do. So we only keep essentially the top 2 fastest. So.
I guess the question from a networking perspective is that when you're connecting into your Tor, right? You got your NIC is connected to a direct port on the switch, right?
Uh-huh.
And that link auto negotiates.
Uh-huh.
Right? And so I'm trying to figure out at what point in time is this a beneficial process, because the link speed of the port connection is really what you're going to be basing that on, correct?
Well, for the multi-channel, the link speeds we get, the client interfaces tells us the client interface speeds, and then the server we query, and then it tells us what it thinks the link speeds are for each of the NICs.
Port link speed, or is it trying to gauge the oversubscription between the client and the server through the topology?
No, we're just going straight by what's reported for the link speed.
Okay, but the link speed is not auto-negotiated between the ports and the switches.
So the question is, where are we actually getting these link speeds, and how do they affect the multi-channel selections? In the SMB protocol, there's actually a specific call that the client makes to the server, and in the reply, the server reports what the link speeds are for each of the NICs. Where the server actually comes up with that data from, it's up to the server. So the server could totally lie and say everything's 100 gig.
But if your client is sitting on a 100 gig switch A, and your server is sitting on a different 100 gig switch B, and there's a 10 gig link between A and B,
So,
The client would say 100, the server would say 100,
yes.
but the link is actually 10.
Yes. So the question is, if there's 100 gig network over here, 100 gig network over here, and a 10 gig in between, yeah, the SMB protocol can't handle
It
that.
assumes it's 100, it doesn't know about the.
Yeah, it doesn't know what's in between.
Right.
And even if you were on, 100 to 100, doesn't mean that the server can actually keep up with 100.
Right.
So, I mean, yeah. I mean, it could be really far away. It could be going over a satellite hop, and yeah.
You detect InfiniBand and RDMA as well? Or no?
The question is, do we support infinity band, RDMA and stuff like that?
InfiniBand and RDMA for,
I don't think Macs have RDMA.
sorry?
I don't think there's any hardware for RDMA for Macs. I think,
You could plug it into a slot, but does macOS support it?
Right.
I'm not even sure anybody's created the hardware for it.
Discovery
Yeah.
connected channels is how you can get packets over InfiniBand using RDMA.
SMB will, the SMB protocol will tell you the type of the NIC and the metrics such as RSS capability and raw bandwidth capability. Whether you can get to those is a question of you, the infrastructure, and everything else.
Right. So,
I didn't realize there wasn't an RDMA adapter available.
I don't think there is yet. I think a few years ago, I was asking some of the RDMA vendors whether they actually had hardware for Macs, and they were like, no. May have changed since then, but I don't know. So, moving on to compression. That is an hard drive-based iPod with 30 gigs of space from 2005. And it's actually the newer one because it has, the capacitive wheel instead of the actual spinny mechanical wheel. So compression. Like everything else, you should always make sure your Windows server is running the latest version to make sure you have all bug fixes. When we're developing compression, we contacted Microsoft and obeyed from Microsoft. They were kind enough to give us example files and then the matching compression or compressed files. And so that actually allowed us to test our compression algorithms independent of implementing it over the SMB protocol. So Obeyed has a whole set of files for that. Just a note, something I tripped over. For the client, for sending out requests, you have to sign the packet first, then you compress it, then you encrypt it. Okay? And on the server side, of course, it's the opposite. You decrypt first, then you decompress if you need to, then you check the signing. Another thing to note is that write data can actually fail to compress. And in that failure case, we actually send the data as non-compressed. And when I say fail is the data actually compresses, but it ends up being larger than the original data. It's like what happens if you try and compress a file that's already compressed. It doesn't work very well. The macOS client, after too many compression failures on write, we will just automatically give up. We'll just say, forget it. This file has too many failures. We'll just write it straight through. The SMB protocol actually allows any request or reply to be compressed. We actually do not do that. We mainly only do the I/O requests, the reads and writes. We do not do any compound calls. Mainly because it doesn't make sense to pay the cost of compressing a packet that's only like maybe 64K or smaller. There is an oddity that on reads, the client can actually set a flag that says, please compress the read reply. But it's just a request. The server can say, nah. But I think that's the only request that the client can actually say, please compress this. Otherwise, it's totally up to the client and server when to compress or when not to compress. What do we support? We support LZ77 plus Huffman, which for our system and my testing, I found it compressed the data to the smallest size, but it costs the most in CPU cycles. The LZ77, it compressed by a moderate amount, but it actually seemed to require the least amount of CPU speed. And then the LZNT1, it had the least amount of compression, but it actually had a medium compression speed. And then the last compression one is called pattern V1. It only applies if your server supports chain compression, and it handles repeating data patterns. So like the beginning of the data block has 50 A's. Pattern V1 will say, okay, well, there's an A and it repeats 50 times. But it only works for chained. We support both chained and non-chained compressions. In Sequoia, compression is currently shipped off by default. And I'll get into that a little bit on the next slides or so. And then again, as I said earlier, only reads and writes are compressed. We don't do like name streams or X adders or anything like that with compression, just basic reads and writes. So non-chain compression, we'll just go over a little bit of how it works. So what we find is in the negotiate exchange, if the server does not support chain compression, it will pick one compression algorithm to use. Pattern V1 is never ever used in non-chained. Again, this is kind of implementation specific details, but we tend to follow whatever Windows does. But Windows leaves the SMB header and the read-write structures uncompressed. And it just compresses the data part. It's actually kind of nice because at least on Wireshark, you can see the more important stuff. So. This is that even readable? I don't know, I tried to make it as big as possible, but that's a non-chained packet. So you have the compression transform header, you have the protocol ID, which indicates that it's compressed. You have the size. This is actually 16K. You can see it's using LZ77 Huffman. Wireshark sometimes can decompress it. Not all the time. There are many times where Wireshark just goes, I don't know what this is, and I don't know why. But when it can decompress it, it shows it up down there. In this particular case, things to note is the offset up in the compression transform header says hex 50. And if you count up the number of bytes, that's to skip over the SMB2 header and the read-write structures. Okay. Okay. It was easy to get all sorts of ones where it just raised its hand and said, I don't know. But this is actually a 16K read, and it's actually getting compressed to less than 426 bytes, because if you look at the length way up on the TCP part, it says length 426. Chain compression. Again, the server will pick one algorithm, but it's always assumed that you also get pattern V1. Again, the Windows adds the SMB header and the read-write structures. They put it in as the first chained element, but then they set the compression to be compressed none. So again, it's skipping the header and the read-write structures. The remaining data is actually processed in chunks. This was a surprise to me. The basic algorithm that you're supposed to do is you check for a forward data pattern in the chunk, and if found, you add the pattern V1 payload. You check for a backwards data pattern, and again, if found, you save that for later. You then compress whatever remaining data you have in the middle. You put that into the chain. If you had backward data pattern, you now add that to the chain, and then you go back and you repeat the process. Turns out that one packet may have multiple chains from several chunks. This is probably one of the biggest chains I saw from a Windows server. Oh yeah, that's like really, really, really tiny. What happens is the first payload, it's that uncompressed SMB header in the read-write structure. The second payload is 256 kilobytes of compressed data using LZ77. There was no pattern v1 found at the beginning. The next 256 chunk is the third payload, and the whole thing was compressed with LZ77. You have a fourth payload. It's a pattern v1 of about 32K. It's actually 32,255 of some character. The next payload is 256 kilobytes. Again, it's another pattern. This is where I actually got tripped up because there was two pattern v1s back to back. And that happens because, as I said, they process in 256K chunks. And I never thought that was possible until this packet hit and my client went, I went, what? But it goes through the seventh payload, again, 256K. If you add up each payload chunk, they're each 256K. Okay? And then it's like the last, I think there's 9 payloads in this one chain. And this was I'm pretty sure it was a read from the server, because the server did this. Windows server. So we added in a bunch of NSMB keywords so that you can control it. If you want to disable a particular compression, you can with the comp algorithm map. If you want to disable chaining, you can disable chaining. The I/O threshold is the minimum amount of the I/O size that will even attempt compression. So if you're doing a read or write of 2K, we're not going to bother. It's just not worth it. We have the compression chunk length. Again, we match Windows. They do 256K. We will stay with the 256K. We have the max fail count. That was where I was saying that as we're doing write data, if we keep failing on compressing it, how many times do we get failures before we finally say this file's not worth it? Because you could have a file that's like a JPEG file, where every time that we try and compress, it's going to fail. Or you could have a file that the beginning part of the data compresses really well. You have just a small section in the middle that doesn't compress well, and then the rest of it compresses well. So it's a minimum threshold of how many times for that entire file can we fail before we give up on compression for that. We have a compression exclusion list and a compression inclusion list. So as I was saying, there are certain files that we already know which are not going to compress well. And it's, again, typically files that have already been compressed. So by default, we have an exclusion list. And we're going by the file extension. So if the file doesn't have an extension and it happens to be a JPEG file, then we're going to try and compress it. So we just look at the file extension as a hint. This is the current default list of files that we automatically skip. Again, most of them are some sort of compression. Those in that previous slide, the comp exclude list and the comp include list allow you to edit that list. So if you're like, hey, our MP4s are really compressible, you can edit the list and say, go ahead and try and compress it. Or if you have a particular file type and you're like, we know this doesn't compress at all, you can add it to the list and we'll automatically skip it. Why do we have compression off? Well, I thought that, gee, if we compressed everything, everything would be faster. No, actually it didn't really help as much as I was hoping. It's very, very situational. It really depends on what kind of data is and how fast is your network. If your network's fast enough, it's just faster to send it. If your network's slow, then compression helps quite a bit, assuming the data is highly compressible. I found that chain, non-chain really didn't affect performance much. Again, it depends on your data. If you have a lot of repeating data, then chain would work well. I'm running out of time, so I have to go faster. Here are a little bit of performance results. We have 2 1 gig channels in the middle, a 10 gig channel, and then a 100 gig channel. And then it's the gigabytes per second. And the AJ, so you have AJA, no compression, and then same kind of color, AJA compressed. So like on 1 gig, it jumps quite significantly. It goes from like 1.7 gigabits per second to like 16. But AJA uses like a 4-byte repeating pattern. So it's like the ultimate in data compression. But and then we have Finder no compression and Finder compressed, which is the greenish ones. But as you can see, as the network gets faster, the differences become less and less. So that was read compression. This is write compression. Again, it's just showing you that slow networks, yeah, it's helpful. But like the Finder files were more like text files. And even text files, we didn't get that much savings in compression. But of course, there's just pure network speed, but there's also bandwidth. And so what we found is, well, this was AJA. Again, it's the super compressible data. The packet count went from, so this is non-compressed, and then that's compressed. The packet count from Wireshark said it went from 12,459,200 packets down to 163,000 packets. And the average packet size went from 1443 to 537 bytes. And then total bytes, well, the amount that we were transferring was 16 gigabytes, so non-compressed would be 16 gigabytes. But with compressed, the total transfer size was 83 megabytes. So again, if you have super compressible data, you can save a lot on bandwidth. This is that text file. It's actually this enwic9 file, which is some standard text file used from compression testing. Again, for the bandwidth count, we went from 723,000 packets down to 267,000. And the total bytes went from 1 gig, which is the enwic9 file size, down to 361 megabytes. So compression helps with bandwidth, but just pure transfer speed, not so much. But again, it sort of depends on your setup. So if your network setup or your files that you're transferring around happen to be highly compressible, then yeah, it's useful.
Question. For the speed testing, you showed like 110 is that are the NIC speeds of both client and server the same, or is that?
Yes.
Okay.
Yeah. So the question was, for the performance results, were the NIC speeds on both the client and the server the same? And yes, so it was 1 gig to 1 gig, 10 to 10, 100 to 100. So the last slide for questions, just want to point out that that is not a true iPhone. That is actually a squishy iPhone pillow that we bought somewhere. Yeah. But questions in the out of time. So I don't know if that was good or bad timing. Any other questions or? You can find me in the SNIA lab downstairs.